In this video, we'll talk about row echelon form and reduced row echelon form and how to determine the solutions to a system of equations from them. So first, typically we take a system of linear equations and translate it into an augmented matrix. After it's written as an augmented matrix, we apply Gaussian elimination or Gauss-Jordan elimination to get it into row echelon form when using Gaussian elimination, or reduced row echelon form when using Gauss-Jordan elimination. So in this lecture, we'll go over how to understand REF and RREF to be able to obtain the solutions for the system of linear equations from them. In a separate lecture, we'll discuss the actual procedure involved in performing Gaussian elimination and Gauss-Jordan elimination. So basically for this lecture, we'll think of REF and RREF as sort of a black box which will help us solve a system of linear equations because the graphing calculator will perform the elimination procedure for us. And then in a separate lecture, we'll learn actually the elimination procedure separately. Okay, so first, let's try to better understand matrices. So a matrix is just a rectangular array in which each entry is a number, and in this course we'll mainly focus with real numbers. So here I have an example of a matrix, and it's a 4x6 matrix. So when we write the size of a matrix, the first number indicates the number of rows, and the second number indicates the number of columns. And I've indicated the different rows and columns here along the matrix, right? So this would be row 1, row 2, row 3, row 4. So the rows go across the matrix, and the columns are column 1, column 2, column 3, column 4, column 5, and column 6 going down the matrix. And typically we denote matrices with capital letters. So I call this matrix capital A, and the individual entries are typically denoted using lowercase letters, and the entries are identified using a double subscript notation. So when I write A sub ij, so I and j are two separate numbers, and I indicates the row the entry belongs to, and the j represents the column it belongs to. Right, so here we have some examples here where A sub 2 3 is the entry in row 2 column 3. Right, so row 2 column 3 meets in this entry, so A sub 2 3 is 13. And then A sub 4 1 is row 4 column 1. Row 4 column 1 is negative 2, so A sub 4 1 is negative 2. And then finally A sub 1 4 is row 1 column 4. Row 1 column 4, which gives us a value of negative 3. So A sub 1 4 is negative 3. So you can see typically when you switch the row and the column, the values typically are different. Right? So A sub 4 1 is different from A sub 1 4. So be careful which is the row number and which is the column number, right? So the first one is the row number, the second one is the column number. Okay, so so that's how you read the entries in a matrix. Okay, so on the bottom of this page, here we talk about how to translate a system of linear equations as an augmented matrix. So we've already seen a little bit of this before. So basically what you want to do is to write the system of equations in standard form. Which means that the variables, the individual variables of the equation should be lined up together. Right, so you see the x's are lined up, the y's are lined up, and the z's are lined up. Some of the equations have missing terms, and that means that the coefficient is 0, right? So here y has a coefficient of 0, and for this equation x has a coefficient of 0. And so when we translate it into an augmented matrix, all you have to do is read off the coefficients. Right, so for the first equation, coefficient of x is -1, coefficient of y is 3, coefficient of z is -1, and then the constant term is 0. And typically we separate the coefficients from the constant terms. And we do the same for the other equations, right? So the second row, for the second equation, the coefficients are 1, 0, 3, -1. Right, so again, the y is missing from the second equation, so that means that it has a coefficient of 0. And then the x is missing from the third equation, so that has a 0 in this entry. Then the other coefficients are 2, -5, 3. Right, so again, for the augmented matrix, the coefficients go on the left, and the constant terms are typically separated. In some cases, we might only be interested in the coefficients without the constant terms. So you can do a separate matrix for the coefficient matrix. As you can see, here I've ignored the column for the constant terms and only have the entries for the coefficients in the coefficient matrix. On this page, we'll talk about what row echelon form and reduced row echelon form looks like. So as usual, we'll abbreviate row echelon form as REF and reduced row echelon form as RREF. Okay, so for row echelon form, there are 3 properties you should look for. Right, so the first property for row echelon form is that any rows consisting entirely of zeros should be at the bottom of the matrix. The second property is that each row for each non-zero row, the first non-zero entry should be a 1, which is called a leading one. And the third property is that 2 consecutive non-zero rows, the leading one in the higher row should be farther to the left than the leading one in the lower row. And another way to say that is that the leading one in the lower row should be farther to the right than the leading one in the higher row. And then finally, so these properties are for row echelon form. And then finally, if you additionally have that every column that contains a leading one has zeros above and below the leading one, then it's called reduced row echelon form. Okay, so here on this page, we have different examples of matrices. Some of them are in row echelon form, some of them are not. So for each of these matrices, we're going to discuss the 3 properties and see why it is or is not in row echelon form. Okay, so the first matrix doesn't have any rows with all zeros. So if you look at property 1, it says any rows consisting entirely of zeros occurs at the bottom of the matrix. But if a matrix doesn't have any rows of all zeros, then property 1 is still satisfied. right? So when there are no rows with all zeros, it's still okay. Property 2, so the leading ones, right? So first entry on the first row is a 1. Here, the first non-zero entry in the second row is a 1. Here, the first entry, non-zero entry in the third row is also a 1, so property 2 is okay. And then property 3, you can see that the leading ones continually go down and to the right. Okay, so it doesn't have to be on a diagonal, on an exact diagonal like this, but as long as it goes down and to the right in the staircase pattern, property 3 will be okay. Okay, so this is in reduced echelon form, but it's not in reduced row echelon form because you can see above these leading ones I have non-zero entries, right? So above here is non-zero, and then above here on this entry is non-zero, so this is not row reduced echelon form. Okay, so that's the first matrix, and in the second matrix you can clearly see that the second row is all zeros, but it's not at the bottom, so it fails the first property. And the leading ones occur here and here, and it goes down to the right. So the second and third properties are okay, but because it fails property 1, it's not row echelon form and also not reduced row echelon form. Okay, so continuing on to the third matrix. So again, doesn't have any all zero rows, right? So, but that's still okay, right? So property 1 is okay, and the property 2, the leading ones, right? So it's the first non-zero entry in each row contains a 1, so property 2 is okay. And property 3, right? So again, you can see that to go from one leading one to the next, it's always down and to the right. But again, it doesn't have to be exactly on a diagonal. So here you can see it skips a column, but as long as it's down and somewhere to the right, property 3 is still okay. Right, so this is in reduced echelon form, but not row reduced echelon form, because again, above these leading ones I have entries that are not zero. Okay, so moving on to the next matrix, we do have a row of all zeros, and it is at the bottom, right? So row of all zeros is at the bottom. So the first property is okay. And then again, picking out the first non-zero entries in each row, these are all 1, so the second property is okay. And again, they form a staircase pattern. So down and to the right, down and to the right. So third property is okay. And then additionally, above the leading ones, there's also all zeros. So the fourth property is okay, right? So it is also row reduced echelon form. So it's both row echelon form and also reduced row echelon form. Right, so I mean, you can have entries that are not 0 or 1 in reduced row echelon form, but it cannot, the non-zero entries cannot be above or below the leading ones, right? So you see how these 3 columns contain leading 1, so all the other entries in these 3 columns are all 0. The last column does not have a leading 1, so it's okay to have non-zero entries there. Okay, so continuing on to matrix E, you can see that in property 2 fails, right, because of the 2 in this matrix, right? So the first non-zero entry in row 3 is not a 1, so it fails property 2, and it doesn't really have the staircase pattern, right? So so the non-zero, so the leading term is not farther right than in row 2. Okay, and then finally, in the last matrix, you can see again the leading terms are not in the correct positions, right? So the leading 1 in row 3 is not further right than the leading 1 in row 2. Okay, so again, these examples are meant to help you understand what to look for when something is in row echelon form or reduced row echelon form. Okay, so one of the reasons why we like row echelon form is once a matrix is in row echelon form, it's not too difficult to obtain the solution from there using a method called back substitution. So basically, row echelon form gives you an equivalent system of linear equations, which we can then solve by substitution. Okay, so here we have an example of a matrix in row echelon form, but not reduced row echelon form, right? Because the leading ones occur in these entries, and above them we have non-zero entries. Okay, so this system is represented by an augmented matrix, so it's a good idea to separate the coefficients from the constant terms, and it's also a good idea to identify the variables, right? So here we have a system of 3 equations in 3 variables, so let's just call the variables x, y, and z, and so let's translate this back into a system of equations, right? So put it into equation form. Great, so again, these are the coefficients for x, y, and z, right? So the first row turns into x minus y, and there's no z term because of the 0, is equal to 3. The second row starts with y minus 2z is equal to 1, and then the third row is z is equal to negative 1. So you can see right off the bat we know the value for z, and so you can see that the second equation is y depending on z. So if we know z, we can solve the second equation from there by substituting. Okay, so this is where the term back substitution comes in. Okay, so you plug in z equals -1. So what is it you get? What do you get? Y minus 2 times -1 is equal to 1. So that means that y plus 2 is equal to 1. So that means y is equal to -1. And then again, we back substitute into the first equation, knowing y. So what do you get? So x minus -1 is equal to 3, which gives you x plus 1 is equal to 3, which means that x is equal to 2. Okay, so with a simple back substitution method, it's not too difficult to solve equations that are already in row echelon form. Okay, so continuing from here, what we're going to discuss in the next few examples is if you have an augmented matrix already in row echelon form, or in these particular examples, they're going to actually be in reduced row echelon form. We want to be able to identify where the leading ones occur, and because basically we want to be able to differentiate when a system has a unique solution versus when a system has no solution versus when a system has infinitely many solutions, and how to determine the solution from there, right? So basically how to understand the solution set from row reduced echelon form. And it starts by identifying the leading ones. Okay, so the first thing to always do is to make sure the augmented matrix is set up, right? So you identify the variables in the system, right? So, and then you also separate the coefficients from the constant term, right? So which I've drawn into the matrix here, and then you can see that it's a system of 2 equations and 3 variables. So I've called the variables x1, x2, and x3. Right, so that's the first 2 steps, right? So understand how the system is set up, and then from there, right, so you go across the rows, so across the first row, across the second row, and because it's in row echelon form or reduced row echelon form, the first non-zero entry should be a 1. So I want to identify where they're located, right? So I've circled the leading one in the first row. I've also circled the leading one in the second row. Right? So again, you identify them by going across the rows. Okay, so once we've identified the leading ones, right, so you can see that the leading one here corresponds to the variable x1. The leading one here corresponds to the variable x2. But for the variable x3, there's no leading one associated to it. So when this occurs, right, so when a variable does not have a leading one associated to it, it's what's called a free variable, right? So I've marked off the note here where it says columns that don't contain a leading one indicate a free variable, right? So the reason we want to identify the free variable is that whenever you have free variables, that will tell you that the system has infinitely many solutions, which is the case here, right? So if you remember before, when you do the elimination process, the free variable comes from when you get some situation where you get 0 equals 0, right? But you can see that it doesn't happen here, basically because the number of variables and the number of equations are mismatched in this example. And so you have to be careful about how to identify when there are infinitely many solutions. So what we want to look for are these free variables. And you don't necessarily need to have a row of all zeros to have infinitely many solutions. Okay, so basically you want to identify this information from the augmented matrix, and then from there we can determine the solution, right? So we know that there should be infinitely many solutions because the free variable x3, and so what you do is just translate it back into equation form, which I've done here, right? So you can just read off the coefficients. This is x1 plus 5x3 is equal to 2, and then the second row is x2 minus 3x3 is equal to negative 1, which I've written out here. And then x3, I've considered the free variable, so I can parameterize x3 by introducing the parameter t. And then from there, I just solve x1 and x2 in terms of t, right? Because if we know x3 is t, you can just plug it into here and then solve for x1 and x2 in terms of t. Okay, so in this example, I've shown you how to identify the free variables and determine that the system has infinitely many solutions. Okay, so on this page, we have two more systems of equations, which we will then put into reduced row echelon form, and again try to understand how to obtain the solutions from the RREF. Okay, so first of all, we're going to take each system and set up the augmented matrix, right? So here we have three equations in two variables, but because of the constant terms, the augmented matrix will be 3 by 3. So let's enter that in. Okay, so it's a 3 by 3 matrix. And again, you can just read off the coefficients, right? So first equation is negative 3, then 5, then negative 22. Then the second equation is 3, then 4, then 4. Then the last equation is 4, then negative 8, then 32. Okay, so this is our matrix, which here I have is called matrix A. Right, so if I never need to access matrix A, I can just go back into the matrix menu. Right, so again, this is my matrix A. So I've put it in as an augmented matrix. The matrix here is called B because I entered it as a matrix B previously, but you can see it's the same matrix. Okay, so here's my augmented matrix. Then we put it into reduced row echelon form. Okay, so if you remember, to calculate reduced row echelon form, you go into the matrix menu. Under math, if you keep scrolling down, you can see the operation for RREF, and then you have to choose the matrix that you entered before. Here it's A, And you can see this is the row reduced echelon form of my matrix. So 1, 0, 4, 0, 1, negative 2, and then a row of all zeros. Okay, so let me enter in the screen capture. Okay, so this is the row reduced echelon form of this matrix. So as before, we separate the constant terms, identify the variables, right? So x, first column for x, second column for y, right? So this is the leading one here in the first row, leading one in the second row, and so x has a leading one, y has a leading one, so there are no free variables. So that means that this system has a unique solution. Right, so one thing to notice is that this system has a row of all zeros, but it has a unique solution, right? So I mentioned this previously, that you should be careful that a row of all zeros doesn't necessarily mean infinitely many solutions. Okay, so again, this has a unique solution, and then you can just read off the solution from the rows, right? So the first row says x is equal to 4, and the second row says y is equal to negative 2. Okay, so we have the solution to this system. Okay, so continuing on to the other system here, we just follow the same procedure, right? So first we do the augmented matrix. Which I've already entered previously. So I'm just gonna put it in here, right? So you can see the augmented matrix is just taking the coefficients, right? So 1, 2, 0. Then second row 1, 1, 6. Then third row 3, negative 2, 8. Okay, so once we have the augmented matrix, we put it into row reduced echelon form. Again, which I've calculated previously. So this should be the row reduced echelon form of this matrix. And so let's separate the the coefficients from the constant terms, identify the variables x and y, and you can see that when you translate the rows, right, so row 1 tells you that x is equal to 0, row 2 tells you that y is equal to 0, and row 3 is 0x and 0y, so that's just 0 on the left, and on the right it's 1. So this tells you, 0 equals 1 is impossible, so that tells you that this system has no solutions. So the situation for no solutions is again basically the same as before, where if you see 0 equals some other number, so a row that looks like kind of like this, then you know that there's no solutions. Okay, so we've seen some examples of what to look for in terms of the RREF to be able to determine the solution for the corresponding system of equations. On this last page, we're going to talk about homogeneous linear systems. So basically, a homogeneous linear system is a system in which all the constant terms are zero, right? So the right side of the augmented matrix is all zeros. So because the right side of the system is all zeros, homogeneous systems will always have at least one solution, right? Because if you set all the variables equal to zero, then anything times zero is just equal to zero, right? So this is called the trivial solution, and so the trivial solution is always at least one of the solutions for a homogeneous linear system. Because we know that the right side is all zeros for a homogeneous system, typically only the coefficient matrix is given, and to get the augmented matrix, you have to add in the additional column of all zeros, right? So in this example here, again, you're only given the coefficient matrix, so the augmented homogeneous system so let's draw it in, right? So the coefficients are 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, and then the right side is all zeros. So this is the actual system of equations. Okay, so this is already in RREF, right? So this is already in row reduced echelon form. So we can determine the solutions from here, right? So where are the leading ones? So the first row is here, second row is here. Right, so let's identify the variables: x1, x2, x3, and x4. Right, so you can see that x2 is free, x4 is free, right? Because the leading one here corresponds to x1, leading one here corresponds to x3. So x2 and x4 are free. So because we have free variables, this has infinitely many solutions. So let's parameterize them. Right, so x2 is free, so I can say x2 is s. x4 is free, so I can say x4 is, say, t. And then row 1 and row 2, I write out the equation for row 1 just says x1 plus x4 is equal to 0. Row 2 says, so that's x3, says x3 is equal to 0. Okay, so that gives us x3. And then x1 is in terms of x4, which is t, right? So what does that tell you? So x1 plus t is equal to 0, which means that x1 is equal to minus t. Okay, so written out in coordinate form, right? x1 is minus t, x2 is s, x3 is 0, and x4 is t. So this is the parametric form for the solution. Again, it has infinitely many solutions in this case. Okay, so let's continue to the second example. Right, so the augmented homogeneous matrix for this one, right? So the coefficient matrix is 3 by 3, so that means it's 3 equations in 3 variables. But then I have to introduce the constant terms, which for a homogeneous system again is all zeros, right? So here there are no leading ones at all, so that means that x1, x2, and x3 are all free. So I mean you can parameterize them as R, say R, S, and T. Right, so it's just R, S, T, but R, S, and T can be anything, right? So basically the solution set is every point in 3-dimensional space, right? So this is infinitely many solutions. And the solution set is all points in 3-dimensional space. Basically, if you take the zero matrix and you multiply it by any 3 coordinates, it's always going to produce all zeros. Okay.